So here we also check it out. I still remember that there are some easy way, because we know that the single normally sp3, double sp2, triple bond, like triple, if you see the triple bond sp. So this is the one of the things to find out, and also the valency electron. See, this is single sp3. So please check it out here. Some example we have, last time we did. Now let's move on to the molecular orbital theory. So if we have the 4 atomic orbitals, that means they are going to make the 4 molecular orbital, or they will make the same types of bond. Now, last time we learned the wave. You remember the constructive wave or destructive wave, and also we saw the probability of finding electron. So there was some node place. We say actually there is no probability to find the electron, but there are also some way place that we have a chance to get the electron. We have also learned that electron actually the kind of wave. Remember, and then we also prove or evidence that electron have a dual character. You remember? So all those things we learn. Today we are going to see that actually why we find those type of node or the place where is no electron, and that make them making, even they have a probability to make a bond, in spite of that they are not making, but other making. So we are going to see it. So valency bond theory predicts 4 identical sp3 hybrid orbital to explain the bonding. So now, if we explain the electronic wave function for this molecule, we find the following molecular orbital. So we guys can see here different types of orientation of these 2 molecules. Some will make the bond, some will not. So some molecular bonds have nodes between the green and pink, and some doesn't have, some make the bond. So how and why, that is the discussion or main focus of this chapter. Let's review here. So actually in phase and out phase, when the electron density is high, both the wave, and that is the reason we say the in phase, and that times they join together and make the high amplitude wave, which is called the constructive wave. And here we have a chance to make a bond of the molecule. But when the out of phase, here the electron density is less. Maybe one have, one doesn't have. Maybe electron in out of phase. I mean, if we consider the hydrogen atom, diatomic molecule, actually this is 2 hydrogen atom bonded, correct? So what type of case here in that we know the nucleus and the electron attract actually. So we may normally see here is the electron. That is the constructive, that there is a possibility to find the electron, and if we have more electron to wave, then their density is high and they can make the constructive wave, and ultimately the bond because of the attraction of nucleus of the atom and the electron. But what happened in case of out of phase or discussions, maybe electron not available here, electron may be in other side. So the force you need to make a bond between the 2 atoms, it's not enough. So in that case, sometimes bond cannot be formed. That's called the anti-bonding. So those type of things today we are going to see. So I hope that you now clear that even when you are going to in the future the geochemistry 2 and thermodynamics, you will be learn more detail about it, that even here is the first row 1 2 3 4 5, these 5 students run the same chemical reaction, same reagent, maybe the 3 students reaction is okay, 2 students fail. there may be chance. Why? You guys have a general question that we use the same thing, but what? There was some internal error that some students' molecule was perfectly come close together scientifically and technologically, how they need to come close and make a bond to form. I mean, the new product, when the new product bond make, that's called the exothermic, correct? Energy release. And maybe there are some reason we cannot see visually some mistake that other two students bond didn't work. So when we are going to now talk the bond and anti-bond, this will be more clear. And also why there is a one more basic reason that I show here. So if we make the molecular orbitals like two atomic orbitals equal to two molecular orbital. Now let's consider to discuss this molecular orbital theory with the example of hydrogen. So I have already told just in last slide that there is let's consider the two hydrogen atom. One is Ha and second one is Hb. Each hydrogen atom has 1s atomic orbital. This 1s orbital can combine in two ways to generate a new set of molecular orbitals. So one way is an in-phase way and another way is a out phase way, out of phase. So in phase we just saw in the last that here in phase means when two wave as an electron, we know that we cannot see electrons are so tiny particles, and scientists will find that actually the electron move around the nucleus as a wave. We also draw like that circular wave. So we find that here that one hydrogen wave, two hydrogen wave have the similar electron density, so they can make the constructive or in phase, and they can make the bonding. But out of phase, the density between the atom can be depleted. How? Maybe one we have the two wave, so maybe one we have electron, but one we don't have it. So if we don't have electron sufficient between the two atom, then the electron and their affinity not enough to make the bond. So maybe the electron look into here. Maybe in that case electron in other side, so they cannot make bond, and this is called the antibonding. So let's go back here now. So that's why we are telling here that let's consider the hydrogen molecule, one atom Ha, one atom Hb. So there is a two types of new set of molecular orbital. One is antibonding and another is bonding. So in phase the electron density will be higher and between atoms, and as a result the bond will be formed. But out of phase the electron density will low or depleted. That's why the antibonding molecular orbital will form. Now after that slide I will go back to the blackboard because I am here because I need to draw something to explain more clearly. But let's see first. Let's consider here we have, so now we know the out of phase nuclear repulsions are maximized and no bond is formed. So nuclear repulsion. So that means we need nuclear attraction, not repulsion. So when nuclear repulsions are maximized, then no bond. When nuclear repulsions are minimized, then the bond can be formed. So actually, what type of force of attraction or repulsion actually go through this in phase and out phase? To explain, let's go back to the blackboard. So let's consider first in phase. So let's consider in phase like a constructive. So we have two hydrogen molecule, and this is our nucleus or proton. So here, this is, let's consider this is constructive, and we have sufficient electron density. So here's some electron for this atom, here's for this atom. So okay, I want to delete this one. That can be confusing. Okay, so let's see that we have. Yes, so we have electron for this atom and we have electron for this atom. They can make a bond. Why? The reason here, the nucleus. So nucleus have a attraction for this electron. So if we consider the attractive force, attraction is opposite of repulsion, correct? So this is, let's consider this is the force of this hydrogen atom nucleus to this electron. Similarly, this nucleus will have attraction for this nucleus is also. So let's arrow like that. And this atom, the hydrogen, second hydrogen atom nucleus have attraction force for this electron like that. Also, this nucleus have some attraction for this electron. And now these two positive sign repel each other. Okay, so if we consider this repulsion force, only two repel each other, go away. Okay, so now if we look into the total force, so here 1, 2, 3, 4 are attractive force, correct, and these two are repulsive force. So when your repulsion going to be minimized, repulsive force, and the attraction force is high, that time more favorable for making bond because they can come close together. And this is the reason that our lecture presentation reasoning that nuclear repulsion are minimized, and that's why the bond is formed. But why? This is the actual explanation for that. Now, if we consider the out of phase or out phase, so just opposite things happen. What happened in that case? Oh, by the way, we can little bit more draw. Here we can show that these are the just like wave, that these are the electron. There is no node. Okay, but what happened in case of out phase? Let's consider draw again the two hydrogen atom. So one is plus, one is minus. Minus means in that case no electron or like that. Okay, so there is this portion is called the node. That means here we don't have electron. So where the electron? Electron may be here outside. We don't know. Maybe this is the out phase. So then what happened? This plus and this minus is coming together this way, the force. At the same time, what is going here? This nucleus and this electron force is going this way. This is going this way, opposite way. So the force, attractive force is going out way. And the repulsive force is increasing close to the nucleus and electron revolving moving side. As a result here, nuclear repulsion maximize and the attractive force is minimum. So this reason, if there is no electron, no attractive force here, then they cannot come close together and make a bond. And this is the reason we will say out phase, these are anti-bonding molecular orbital, and here we will be telling the bonding molecular orbital. So, do you guys now understand that why the bonding and anti-bonding molecular orbital is coming? So, the reason is that the same the in phase and out of phase. And in phase and out of phase, we already learned that when the electron density between atom is enhanced and sufficient. But somehow, if the electron density is not sufficient, like one atom has, one atom doesn't, that time the constructive or destructive force happen, and as a result, step by step, this type of molecular orbital forms. Next. So that means if the two hydrogen atom can make the two molecular orbital, but two are not active. One is bonding, another is anti-bonding. Now look into here. So 2s orbital, two molecular orbitals. And we know the S is sigma molecular orbital. So obviously it will be two orbital, but one will be anti-bonding and one will be bonding. So now look this the physical appearance. So here the reason that we don't have sufficient electron, this is the called the out phase or destructive, and this is empty space where you don't have possibility or probability to find the electron. That's why it cannot make a bond. That's called the anti-bonding molecular orbital. And also please make sure that you will also see the anti-bonding as a star. So sigma 1s, sigma star 1s. So when you will see sigma star 1s, that means this is anti-bonding. Now let's consider the hydrogen molecules energy levels. Whatever we saw here, compare the energy level graph. So if we look into this way, energy is low to high. And we know the hydrogen is only one, and this is the 1s and maximum of 2s. So here what will be happen, the 1s, so the electron will be, for the two hydrogen atom, electron will be paired like that. First shell, electron will be paired like that, and this is the lower energy state. And here the higher energy state. And if you look into here, the lower energy state form a bond, but not the higher energy state. So why? Because if the energy is decreased, bond length is decreased. Energy decrease, bond length is decreased, and stability is increased. And also the reason, we know that when bond form, the exothermic and energy release. Now let me know, this is also a natural process. As for example, hike up the mountain and from mountain to go down. Which one is natural and easy? Top to down, correct? Yeah. So here is also same. If you have a less energy, your stability is high, and this is more favorable to make a bond than the higher energy, because higher energy a higher energy situation, like with increasing the bond order. Bond order means single bond, double bond, triple bond. Remember the last time we discussed. So as I said, also the single bond, the rotation is very easy. Double bond, triple bond, the pi bond comes, and those type of bonds, they are so tight that it's very difficult to go and then make a new bond form. So this is the reason that lower energy, remember, lower energy always favorable for making the bond and compared to higher energy. So now I will write something. You guys also can note it down, because sometimes little things make a confusion. So bond order, sorry, increase. Bond order means single bond, double bond, triple bond, okay? Bond order increase, stability increase. Energy decrease. And bond length decrease. Bond length decrease. This is also the, I think you have one chapter, the exam. You remember, I also made a question. Single bond, double bond, triple bond. But if you consider the length wise, single bond is higher length. And number of bond increasing, length decreasing, but their power increasing. Yeah. So please remember these things. Now we will talk about the bond order. We already calculated how bond order. Here also have we can calculate. This is also straightforward, but let's see here a little bit of. So bond order equal to bonding electron minus anti-bonding electron divided by 2. Now in this case, this is for the hydrogen. In case of hydrogen, we have bonding electron 2. And we have, if you look into here, this is called the molecular orbital energy diagram. So if we look into here, we have only 1 for the anti-bonding. So 1 and 1. So that will be repealed because only we have here 2. So here the bonding electron 2 negative, we don't have any anti-bonding electron in that case. So divided by 2 equal to bond order 1. The bond order is consistent with the single bond predicted by the Lewis structure. So another way to predict your bond order, if you think that I don't want to waste time, so always remember the single bond. This is not, there is an exception that it doesn't follow, but single bond, bond order 1, double bond, bond order 2, triple bond, bond order 3. So this is how sometimes we calculate the bond order and the molecular orbital. Now let's draw the molecular orbital diagram for the hydrogen anion. This is just kind of prediction. Now what happened? Here we have 2 bonding electron because we know hydrogen, the atomic number is 1, so electron is 1. So that's why we don't have any anti-bonding electron. But let's assume this one. We know the positive ion, cation means donate the electron, correct? And anion means take the electron. So in that case, -1 means we had to, but we also have another extra, and this is the anti-bonding. So in that case, the bond order for this hydrogen anion will be 2 minus 1 divided by 2. So it will come 0.5. So this is how you have to be considered. We can use the molecular orbital theory to predict the stability. Here I already explained you, so you know. Because when you know the bond order, you know that it will be single bonded, it will be double bonded, or triple bonded. So you remember that just I wrote, I'm going to write one time more. So to avoid the confusion, so bond order increase, stability increase. Because I know that when you are going to be sit for exam, there will be so many topics. So if you guys little bit of review like that, you are not going to be have any mistake in this type of question. So that's why I am repeating these things. Energy decrease and bond length decrease. So here they are talking about the same, but here the helium 2, He2. In that case, in case of helium, there is no bond between two helium hydrogen, and that's why it is not stable. Molecular theory predicts that experimental observation. Now, if you ask that, oh, helium is also two, so why they are not? Because they do the experiment and they find, and this is their diagram. Now, lithium, no bond. By the way, here I have one more thing to explain. Here, your slide have a question mark. Do core electrons participate in a bonding? No. Core electron never participate in bonding. I just want to remind you for those students who forget that core electron means the inner shell electron. We all talking about the bonding and mostly the valence electron. Okay? So remember the core electrons is the inner shell electrons. They have no enough things to come close together, and they cannot make the they cannot participate in bonding. So here core electrons, see one is here, are generally too low in energy. You know, we know that so high energy not favorable. We need the minimum energy. But even if you don't have totally no energy, that's also not favorable to making the bond or participate in making bonding. So please remember that this slide is very exam material. That why the core electron, maybe the asking question that core electron make a bonding, or if it don't make a bonding, why? So the reason is here. Okay. So this is the another point, important slide and point of view. So, okay, do core electrons, yeah, we already see, and why this is the more particular for this lithium they calculate here. Now today we are going to learn the very fun, important things. So you will be 100% master of electronic configuration after today's learning. We will do some practice today. So be able to draw the molecular orbital diagram for any homonuclear diatomic molecule or ion and use the ladder to predict what they are telling. As I said, I two times repeat. Please keep in mind: bond order increase, stability increase, energy decrease, bond length decrease. If you know here, then let's move on. Here it is called the molecular orbital ladder. You don't need to memorize. If we make any question on that, we will provide this ladder. But you need to know that which one is the bonding and which one is the non-bond, anti-bonding, correct? We have already learned that if you have a star, that's our anti-bonding. Okay, so you need to see how many bonding and anti-bonding, and you need to count the electron. Like here we have two, here we have two, here single two, correct? So this is how we have to count. This is for the B2, C2, N2, O2, F2, all are diatomic molecules. But before going forward, I want to practice with you guys how we can write this molecular orbital ladder, or we can, you know that during the electronic configuration, we also write 1s2, 2s2, 2p6. How we can write in this way, we will now practice today. We will have couple of practice. This is not into your presentation slide, so but I think that if you know this one confidently, it will be helpful through all your chemistry life. Your future chemistry life will be easy. Your configuration of this course will be easy, and you will be very confident when you are talking about the configuration. So let's do that, and you guys can note it down, and it will be also recorded here. So I will go back to the blackboard. Okay, let's start with the, we already see the some examples of hydrogen, so we don't need to go there. Let's start with the nitrogen. So nitrogen, we know the atomic number is 7. Sorry. This writing is very difficult using the mouse. And this is mass. We also know the atomic number means the proton number, and with the exception of isotope, atomic number also means the same number of electron, correct? Same number of neutron. You must have the question tomorrow on basis of that, because you guys have a chapter, correct? So it will also be very helpful for tomorrow's exam. So let's see, if we want to write the configuration, we know how we will write. 1s2. You guys are allowed to take the periodic table. However, this is not so much heavy. 1s2, then 2s2, then 2p6. But how many we have? We have 1s maximum 2, 2s2 maximum 2, so 2 to 4, and we have here remaining 3, correct? So 2p3. Now remember that s orbital, when we are going to write this molecular orbital ladder or this electronic configuration this way, so like 1s, this is always 2, and it always have to be opposite spin, like that. Then you have, then you have 2s. 2s also 2, and 2p orbital always 3, px, py, pz. So when you guys are drawing like that, this is p, but you guys will do like that, always 3, like that. Now let's write 2x2. We always know the opposite direction, but when we are going to fill the p orbital, first you need to do like single and parallel, like that. This is 7. So if you look into now here, what you have? 2, 2, 4, 3, 7. You remember one more term we learned, dimagnetic and paramagnetic. When the electron here as a 2 in opposite direction pair, they are dimagnetic. If the electron is like ampere, this is called the paramagnetic. Okay, this is also revise of your exam materials also. So now if you look into same electronic configuration, you can write this way also. Always remember that when the s orbital, they always fill, correct? So you have to write like that. We will do some more example that will be more efficient for practice. So in that case of nitrogen, only 7. So we will be stopped here. Now let's go back to the, I think this is, you okay? Yeah. Now the thing, if this is not 7, if this is any other that have a 8 or 9, let's consider 8. So how you did? If this is 8, you first do like parallel single, and then you have to again come as a pair. So like that. So let's move on for the next example. Magnesium 12. And actually the 24.3. Remember, when you calculate the math problem related to how many electron number, how many atomic number, or proton number, neutron number, please do not only depend here, because we have so many isotopes. In that case, you have to follow the rules like proton number subtract, you need to subtract from neutron, and then you are going to get, in that case, the exact number. That in the quiz I also gave you, and there are few students who was tricked on that. So now if we write the electronic configuration, what we are going to get? 1s2, 2s2, 2 to 4, 2p6, because we already have 12. So 2 to 4 and 10. So that means we have to go again 3s and 2. So now if we want to write like spinning how the electron resides, so we will do the same. 1s opposite 2s. So 2 to 4 already gone. We know the p comes in a px, py, pz. So we have already 6, but when we will write, we will follow the this will be also parallel same. So like that. So then we have 3 more. So then we will write like that. Now we have to go 3s and we have 2. So if you now look into the magnesium, this all in a pair, correct? So this is the molecular, the bonding ladder, and also the configuration, and also this is diamagnetic. Oh, sorry. Now let's see the another example. We will do the couple of examples because I need to show you one exception, because sometimes we talk that when we do the electronic configuration there are so many exceptions. So why exception? Now I will draw two more, then you will find out. So let's do for the phosphorus 15. This is 31 actually. So in case of phosphorus 1 is 2. You can also get some same thing from the periodic table, but you need to know that how to translate these things. 2p6. So this is 15, correct? We know the s orbital is always maximum 2. So 3 is 2. Now count how many? 2 to 4, 4, 6, 10 to 12. So still we have 3 more. So we will write 3p, 3. So now, if I ask you guys to draw, so how you are going to draw? Let's draw with me. So 1 is similar. So 2 opposite spin. 2 is now 2p6. Sorry. We have 3s2. And 3p3. So this 3p3 we need to write like that. And this will be, see, now we can see this is unpaired and it will be paramagnetic. Now got it, guys? So if you have this type of question, you can answer confidently, correct? Yeah. I will show couple of more. We saw that how the atom we can write it. Now, if we have anion or cation, how we will be adjust? Because you remember that I gave you one question, the potassium. Remember the ion, and there was another question I give you to find. You guys, some student was confused that it should be the neon 10, but actually there was no neon. So that was the sodium ion, because sodium was 11. So sodium donate 1 electron and then go to the 10. Okay. So if this type of question, now I will show you some example here. You guys will be more and more clear that why this type of things happen. So let's consider, we know the sulfur is 16 and 32. Now if you have sulfide ion, sulfide, that is -2. What does it mean? First, let's clear. So we know the sulfur have a 16 electron, correct? And And -2 means sulfur also take the 2 more electrons. So that means you have total 18 electrons. So if you ask to write this type of configuration for the S-2 ion, then you have to consider 18. But if you have to ask for the 16, then it is normal 16. Now got it? So now if we write for the 18, how it's going to come? I mean, we don't have too many things in this chapter, but I focus that here because you will be very confident for other chapters as well when you answer. So keep patience and practice with me. That practice are enough that I show you. Yes, total 336. So that will be enough. You will never forget these things. So let's write. For 18 we are writing. So 2s, same. If you write like that, this is also correct. Okay, so don't mind about it. So 2p p3, correct. So okay, I didn't write the 1s2 2s2 because we can also do here now. We practice a lot. So first go the like that and follow the same rule will make your life easy. You know, some people say, some successful people say that success comes from habit. That's true. If you have a routine or habit into your life, you know what to do. You have when you wake up in the morning and until you go to the bed. So that's correct. Rules and habit helps people to become success. So let's see, 2 to 4, 4 or 6, 10. We still have 8. So let's we have to go 3s2. So here we will have 2 more. 3s2. So how many we have? 2, 2, 4, 6, 8, 10, 12. So we have 6 more. So 3p6. So again we will follow the same. Now if we count here, 2, 4, 6, 8, 10, 12, 14, 16, 18. Now if this is anion, we can see this is dimagnetic, correct? But if we just think now, this is not the anion, this is just S16. So how it will be? Got it, the difference? And then the answer will be paramagnetic. So I hope you guys all got it. This is nothing complicated. Okay? So this is how we have to find out. Similar you have for aluminum. I will not do this one. You guys can do aluminum +3. So normally aluminum 13, okay? Aluminum normally 13 atomic number. +3 means aluminum donate 3 electron, correct? When they donate, so you have to be 13 minus 3, correct? That time you have to do the 10. So if you do the 10, I will not write all. I will just change the color to show the aluminum. So let's consider the aluminum 10 and this is red. So 2, 4, 6, 8 and 10. So it will be diamagnetic. We don't need this here. But if we consider 13, so what will happen? In that case, let's change color. Magenta. So let's consider the 13. So in that case, 2, 4, 6, 8, 10. Here will be 12 and here will be just only 1. Correct? If we have a 13. This is how you guys have to be figure it out or write this type of ladder. and the configuration. Last one, I'm going to show the exception one. Why sometimes electronic configuration doesn't follow the rule. So, like I still remember, he came with some example, the maroon color T-shirt. So let's see, this example will make your answer. They will give you answer. So this is the exception one. So write down the cobalt. This is the transitioning metal. This is +2 if we consider. And the cobalt actually the atomic number 27. +2 means 27 minus 2 because they are donating 2 electrons, correct? So we have to draw for cobalt 25. So here I am going to write the electronic configuration. It will make you easy to understand. So 1s2, 2s2, 2p6, 3s2, 3p6. First count how many we have here. 4, 10, 12, 18. We have 25. So we have to go 4s2, and I want to make sure that in the D level you have 1, 2, 3, 4, 5. I mean P level like Px, Py, Pz. So similarly D level you have a 5, okay, sub level. So anyway, the number of electrons remaining, we have 3d7. So 4, 10, 12, 18, 20, 27. So this is for the first, this one. We will go there. So now, if we consider our general rule, from where the 2 electrons should go? According to the rule, we will consider that from here it will go, correct? Huh? They will, yes, they will donate the 2 electrons. So can you tell that from here it will go donate, or from here they will donate? Yes. Though the 3D is the last, but 4s is the higher than the 3D. And this is the exception, okay? So the electron out from the higher energy level, okay? Though in the periodic table, 4s, 4d, but normally we know the outer shell is the valency. So we often miss here. This is not the rules that generally we write, correct? We always give away from the outer. But here's the exception, that you have to know that it will go from the 4s. So that means that if you make your configuration and if you minus the 2 electrons from 3d7, it's wrong. So actually the donation will be from 4s 2. So actually then for the cobalt 25, change the color, cobalt 25, we will write 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, and 3d7. So when you will write, you will follow the same. Got it? When you will, yes.
I understand it's the exception, but from all the charts, it still seems that 4s is still a lower energy level than 3d.
Yeah, but actually the 4s is the high energy level, in fact, and that's why this is the exception. That's I said. Normally the outer shell is the valency shell, and normally from the outer shell the electron goes. But in that case, the 4s is the higher energy, and this is the exception one, and this is you need to be that I say that when you will write If you minus from 3d7, it will wrong. But that's you need to be remembered. This is the exception case. So then you have to do the same like 1s2. Let's just write 2, 2s2, 2p, 6, 3s2, 3p6. Now, when the come the 4s, we cannot write the 4s. We cannot take the electron from here. We have to be keep the empty, and then we have to be 5. D have a 5 sub level. So like D1. Sorry, let's do here. So 2, 3, 4, 5. So you have to be feel the similar way. So the first 1, 2, 3, 4, 5, and then this. So that means this is paramagnetic. This is the exception one. Okay. So not only this, similarly, I think you have iron, you have some other. So that are the exception, and you guys need to be know that. So that was the practice of molecular ladder and also the configuration, how to write this way. I think now you guys are the master on that. It will be recorded here, and let's go back to our lecture. Yes. Now the life is so easy, huh? After this practice, you will never feel this is tough, huh? You have to just know the symbol and you need to count it. Then you can find out. So this molecular ladder will be given to you on the exam. Your job is to know how to use them to predict the bond order. Now you know that which are the bonding electron, which are the non-bonding electron. So you will follow the rules. The bond order equal to bonding electron minus the anti-bonding electron divided by 2. Got it? Let's do the practice. Based on the molecular orbital diagram shown below, what is the level 2, this one. What is the bond order for the following X2 molecule? So for the X2 molecule, then let's see how many we have. For the X2, like that. And we have here antibonding, here antibonding, here antibonding. So let's move on and see how we will count it. Bonding orbital, we have here, we have here, we have here, these three. See? This one, so this one. So this, I don't know, you can take this one. Yeah. This one, see? 2 electron, count here. Pi 2p, how many? 4 electron, 6, and here we have 2. That's why total 8 electron. Got it, guys? Everybody got it? Yeah. Now, antibonding orbitals. How many we have? 1, 2, 3. Let's count the number of electrons here. Sorry, 2, 1, 3, and nothing. So 8 minus 3 divided by 2. Got it? So this is how we have to do. Let's move on. We approximate molecular orbitals by taking linear combinations of atomic orbitals. So this is how we can also check it out. If we have this type of linear, that's antibonding. If we have bonding, this is called the sigma bonding. And this is also called the LACO, linear combination of atomic orbital. Now I want to tell you something. You remember I drawing something and show you that two hydrogen atoms and inside the electron and how the attractive force, correct? Nucleus, electron, huh? And the outside. Same thing is here now. Look into here. How we can check the sign and how we can predict that is this the head-to-head sigma orbital or side-by-side pi orbital. Okay, that we are going to read here. See here. Yes. P orbital overlap to give, if the head-to-head S orbital or head-to-head P orbital will give you sigma bond. If are only side-by-side pi orbital overlapping will give you the pi orbital, pi bonding. Yeah. So let's see. P orbital overlap to give sigma and pi molecular orbitals. As I said, it depends only the head-to-head or side-by-side. Now, head-to-head overlap. Look into here. In the last lecture, couple of times I show you. See here? And this is called the bonding. And if they have a loop, they don't have electron here. That means destructive, okay? Out of phase. In that case, the antibonding will come. Got it? Similarly, let's go back. Go to the next. See, and actually, the 3D representation is like that. It's antibonding, destructive, and bonding, constructive. In that case, if you have a loop, then antibonding. If you have enough electron, they will come close together. Attractive force will be enough between the nucleus and electron, and they will make the bond. Got it? Sigma P and anti-sigma P. Lower energy, bond formation, higher energy, antibonding, the loops, no bond, destructive. This molecular orbital shown to the right arises from, for me, it's a head-to-head P, correct? Let's see. Constructive head-on to P orbital. Okay? Here we go. Side by side P orbital and pi bond. These are, we know, linear. And that makes actually sp and sp2. So that will be look like that. So look into that, yeah. And how the two antibonding molecular orbitals are formed here. Out of phase addition antibonding. Yeah. In phase bonding. Yeah, so that's the things. And we will check out some more questions, and that's all for this chapter. And I will say that this is this last three chapters, especially 10, 11, 12, was like that. But when you will finish the lecture exam 1, please sit on review. And I'm confident that final exam will be also good, because we are learning all the basic that we need and in detail. So it will be helpful for your final exam too. I still didn't see, maybe before the final exam I will go to the department and I need to pick out, but I believe that the way I'm explaining. It should be fine if you practice. And it's very simple that, we have experienced so many years and you are the beginner student. So when I will teach you something and your job to go back home and find half an hour, 1 hour uh, to practice. I mean, if you just, for tomorrow is fine, but this is your regular job because you are the beginner. If you just take a class and then leave it, and before the final exam you want to review, then the topic will be very hard. Yes. But if you take your 20 minutes time, the day you have a lecture, and then you review, you will never forget that. And that's really save your time. That will be saving your time. And this is the thing that I follow from my childhood. Yeah. And this is fact actually. This molecular orbital shown to the right is called, I think this is the pi. Yeah, see? Pi 2p, yeah. When you will see, you will find it because this is the linear one. You need to see it. Yeah, yeah. Just practice. Your presentation is very nicely and explained well lectured here. Yeah, this is the another one. You have to just check it out and practice. Paramagnetic, diamagnetic. Now you know why. So I'm not going to give you the, as we said, we are not going to ask you to draw this, or we are not going to ask you to ladder. We will give you those. You need to read and you need to answer. Okay? So that's not tough. Yeah. 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 So please practice. Some may be, as I say, that we will provide you ladder if we make this type of question. We will give you this if we ask you that which one is energy. The now I am lecturing, so it seems easy, but if you don't review, you may forget. So if we give this type of energies increasing from low, so we can ask you that this is the circle one, is this the paramagnetic, is this the bonding molecular orbital, which one is the anti-bonding. So this type of question, we are not going to give you the ladder, we are not going to ask you to draw. We will give you all. You need to just find the correct answer. If we give this type of question, we have lots of option questions. Yeah. So, yeah. So that was all for your topic 12. Here I want to show you something. This is sp linear, nitrogen, oxygen, and Cn. So actually, both have a similar pattern. Yes, for both. Consider, yeah. I'm not going to press you too much because tomorrow you guys have exam. Leave here. Your lecture is recorded. After finish your